All right, so here on page 11, we're going to be talking about scientific notation, and it's pretty quick. We're just going to be filling in the top half of page 11, but I need to kind of tell you in advance, I want you to attempt these three problems, these three examples that I am not doing in this podcast. I'll remind you of that when we get to them, but you will not get a stamp if they are blank. I just want to see where you're at with them. Even if they're wrong, we'll start by going over them, but we need to make sure that you fill those in to get your stamp in class. So, what is scientific notation? I know it generally seems like a complicated thing, but when it comes down to it, it's a way of writing numbers that are either too big or too small to be easily written in standard form. And easy is kind of a matter of opinion. You could write 10 in scientific notation, but most of the time we save that for numbers like 100 million, which there's so many zeros that we just don't want to write them all down. So the standard, scientific notation is always going to be some number, which we're going to call kind of A here, times 10 to some other number B. And A is what we call the coefficient or the base of the scientific notation, and B is the exponent. And so when it comes down to taking a standard number and putting it in scientific notation, the first step is kind of figuring out our A, our coefficient. So we're going to take whatever our normal number is and move the decimal until it's after the first non-zero digit, and that's important. There are some other notations where it's not after the first digit, but scientific notation, the decimal has to be after the first non-zero digit. And then look at the rest of the number and find all of the sig figs, because the sig figs are going to be the only part that we keep in our base. So we don't keep anything that's not a sig fig. So that's, like I said before, we don't want to write all the zeros if we don't have to, if they're not sig figs. So we move the decimal, this becomes our base, put times 10 after it. And we always are going to have times 10 after the base. And then the next step is to figure out our exponent. Well, in order to figure out that exponent, you need to count how many times the decimal moved from its original place into the place where we put it. And jumped ahead. And that's going to be your exponent. So the number of times that it moved goes on that 10 as a little number up in the top right corner. Now, we do need to keep in mind the sign of that number. If the original number was larger than 1, like 100 million, then that's going to be a positive exponent. You don't even really have to write the plus sign. If it's smaller than 1, if it's a decimal number, the original number had zeros up in front of it, then the exponent is negative. And that's what I kind of keep in mind. There's all of these rules that I've heard about moving it left versus right, but then it's the opposite when we're going out of scientific notation. So this is going to be true no matter what. Larger is positive, smaller is negative. So let's look at a couple of examples. I put that summary of our steps up there at the top. And now we're going to start with this 3 million number. The first non-zero digit, as we're reading from left to right, is 3. So that's where our decimal is going to go. And the at was actually the only significant figure. None of the rest of these zeros were sig figs because there wasn't a decimal at the end. Remember, trailing zeros are only sig figs if there's a decimal in this number. So we're just going to keep that 3. You can either write the decimal or not. It's up to you. It doesn't change anything. That's our base. Then there's times 10. Then we need to count how many times the decimal had to move from where it was, which was understood to be at the end of this number if it wasn't written, to where we put it. And that's 6 times. So that means our exponent here is going to be 6. And that is going to be a positive 6 because 3 million is larger than 1. So 3 times 10 to the 6th is that number. With this next example, moving from left to right, the first non-zero digit is the 1. So 1.2, those two non-zero digits are only sig figs because leading zeros are never sig figs. So 1.2 is our base times 10, and then we need to count how many times this moved. 2, 4, 5, 6, 7. But because this number is less than 1, it's a small number, that's going to be a negative 7 as our exponent. Moving on down, from left to right, our first non-zero digit is 6, so that's where our decimal is going. And these two zeros are both sig figs. Sandwich zeros are always sig figs. And this trailing 0 here is a significant figure, even though the decimal's all the way up front. If there's a decimal in the number, then that trailing 0 is significant. So this time our base is going to be 6.030. Put our times 10 there, and now count how many times we had to move the decimal to get it to its new place, and that's 3. And once again, this is smaller than 1, so that is going to be a negative 3 exponent. Last example I'm doing with you. From left to right, the first non-zero digit is 8, so we're going to make it 8.79. These two trailing zeros are not sig figs because there's no decimal anywhere in that number, at least the original number. So our base is just going to be 8.79. Put the times 10 after it. And then to get that decimal where it needed to be, we had to move it 4 times. And this number is larger than 1, so that it is going to be a positive 4 there. So, looking at these last two examples that you've got over on the right side, I will point out that they are both numbers that the original value is smaller than 1, so they're both going to have negative exponents. Do your best with these, but you need to do them in order to earn your stamp. Now let's just do a couple of examples where we're taking scientific notation and turning it into standard. There's not really any real instructions on how to do this in your packet. If you want to write down what I have in purple here, you can, but it's really kind of easier, in my opinion, than turning things into scientific notation because you're just following what that exponent tells you to do. The exponent tells us how many times we had to move the decimal to get it into this form, and so that's going to tell us how many times to move it to get it out of this form. So I always kind of start with that number there, and then this times 10 to the 5. So we've got the base, 1.86. Times 10 to the 5 means we're moving this decimal 5 times. And keep in mind, because that's a positive 5, I want to move it in the direction that's going to make this number, this value, larger. So if I try moving it to the left, 0.1 is not larger. So that's not the direction we're moving it. We're going to move it to the other direction, to the right. And there's two numbers here, but I'm supposed to move it 5 times. So if I do move it 5 times, there's going to be 3 times that I move it to its place where there's no numbers. So we've got to fill those in with zeros. Those were some non-sig fig zeros that we just had to get rid of. Now cleaning it up, that gives us an answer of 186,000, whether you write the comma or not. Same over here with our second example. Start with our original base. This time I'm going to have to move that decimal 7 times, and because it's a negative 7, I'm moving it in the direction that's going to make my number smaller, which is the left. So I'm going to move it 1 time past the 5, and then these next 6 times, 2, 3, 4, 5, 6, starting to run out of space, I'm going to have to be filling in those empty spots with zeros. So I like to put a leading 0 there because it helps me see that decimal better, but we have 6 zeros and then 5, 2, 0. Don't even think about that last 0 there. It had to be a sig fig. It had to be included in that original number in order to be a sig fig, so it has to be part of our final answer as well. So this one, pretty easy. We're only moving the decimal 2 times. Make sure you're moving it in the positive direction, just like we did together, and you should have no problems.